In this lecture, we will be talking about non-exact equation and integrating factor. So, we have already seen the definition of exact ordinary differential equation in the previous lecture. The definition says that the equation of the form m dx plus n dy equal to 0 is exact if there exists a function f having a second order continuous partial derivative and satisfying the condition m is equal to dou f by dx and n is equal to dou f by dou y. Now, if this condition fails to satisfy, then the given differential equation is non-exact. But to check whether the given equation of the form m dx plus n dy equal to 0 is exact, we use a very simple result. That's a necessary and sufficient condition for the given differential equation to be exact. And the result says that let m and n be a real valid function which have a continuous first partial derivative on some rectangle R. Rectangle R because you are talking about two m and n are the function of two variable. So you defined it on a rectangle R. The equation m dx plus n dy is exact in R if and only if it satisfies the condition dou m by dou y is identically same as dou n by dou x. Dou m by dou y is identically same as dou n by dou x. So this is a very simple result to check whether the given differential equation is exact. Now, if this since it's a if and only if condition, the given equation will be not exact if and only if this dou m by dou y is not identically same as dou n by dou x. So that's a very simple result which we have next. Okay, so now we will take one example of a non-exact differential equation. Consider an equation y dx plus x square y minus x dy is equal to 0. So if you compare it to the general form, here your m is same as y and n is same as x square y minus x. And so when you see dou m by dou y, you have to compute only dou m by dou y and dou n by dou x. Dou m by dou y is equal to 1 and dou n by dou x is equal to differentiate with respect to x keeping y constant, so that's 2xy minus 1. You can see that they are not identically same. As a function they are not equal. They might be equal at some point, but we want to show that they are we want to see whether they are identically equal or not. So here they are not identically same, so this says that the given equation is not exact. Given equation is not exact. Non-exact or not exact. Okay. So now the question is, can we convert the equation, any equation of the form m dx plus n dy equal to 0 as an exact equation? And to answer that question, we first define the term called as integrating factor. What is integrating factor? See, if we have a differential equation m dx plus n dy equal to 0, okay, and if it is not exact in rectangle R, but when you multiply certain function nu to the whole integral to the whole equation, this equation after multiplying by certain function nu is exact, then we say that the function which you are multiplying is called an integrating factor. If you remember, in a linear differential equation we had a term integrating factor as e raised to integral of a of x dx, where a of x is the coefficient function of y in the linear equation, because after multiplying that, the given differential equation gets converted to exact equation, wherein we can find the left hand side as a derivative of certain function. Okay, so after defining this, now the question is, can I convert every differential equation of the form m dx plus n dy equal to 0 into exact by multiplying certain integrating factor? So that is the very important question that we have next. So the answer to this is yes, but provided the given equation have solution as solution. So we will try to justify this by by actually constructing the integrating factor for a equation of the type m. So consider m of x comma y dx plus n of x comma y dy equal to 0. Let you know that the solution is of this form: f of x comma y equal to c be solution of 1. So differentiating with respect to eliminating c, that is by differentiating this function, we have dou f by dou x into dx plus dou f by dou y into dy is equal to 0. Now since this f is a solution of the given equation 1, it has to satisfy this given equation 1. So if you compare this equation 1 to the equation 2, this m should satisfy, this m should be equal to dou f by dou x, and this n should be equal to dou f by dou y. So in the next line, so comparing 1 and 2, comparing 1 and 2, we get, so you get basically what is happening here is that from the first equation dy by dx is same as minus m by n, and from the second equation you get it as minus dou f by dou x, right, minus dou f by dou x by dou f by dou y. So from this two equation you get, that is, I can write down, that is dou f by dou x, dou f by dou x by m. So I'll write it down in this way: dou f by dou x by m is equal to dou f by dou y by n, which is same as, I'll call this as some function, because this is a function of x and y. From here we get this, they are equal. I'll call this as nu, and I'll prove that this is the required integrating factor. So thus I have dou f by dou x is equal to nu m, and dou f by dou y is equal to nu n. So multiplying 1 by nu, you get nu m dx. So we will check now this nu is an integrating factor or not, is equal to 0. Now you know that nu m is same as dou f by dou x into dx plus dou f by dou y into dy is equal to 0, and this is the required, this is the exact equation. As you know that we can find some f, this can be written as total derivative of f is equal to 0, which is exact. Okay. And this is the way we convert given any non-exact differential equation having a solution to an exact equation by choosing a right integrating factor. So let's take an example, the same example, and see what can be the integrating factor for that. So this is the example which we have already discussed, and we proved that this is non-exact. The given equation is not non-exact. Right. Now integrating factor is already given, so we will just try to put this and see whether it gets converts to exact equation. Multiplying new, so we are verifying in fact over here whether this new is an integrating factor or not. We get the equation will be 1 by x square into y dx plus the term over here will be y minus 1 by x into dy is equal to 0. So your m is 1 by x square y and your n is y minus 1 by x. Just check whether they are exact or not. For that we will have to see whether dou m by dou y is same as dou n by dou x. In this case, dou m by dou y, you keep x square 1 by x square as a constant, so you have 1 by x square, and dou n by dou x is same as y is a constant, so derivative of minus 1 by is 1 by x square, so dou m by dou y is equal to dou n by dou x. Hence the given equation gets converted to an exact equation. See, you are simply multiplying an integrating factor, so you know the method how to find the solution of an exact equation. So basically what you will do is that by certain multiplication of a integrating factor, you will convert the given non-exact equation into exact equation, and you will find the solution of this given equation, which will basically ultimately form a solution for the given equation. Okay, as you are simply multiplying a non-zero function to the given function, so it won't make a big difference. So that's it for today's video. Next we will describe all the rules wherein we will see how we can convert the given particular differential equation of the form m dx plus n dy equal to 0 into exact equation. Thank you for watching this video.